So what do we do for a common collector? Anybody remember the circuit? We'll get rid of this transistor, we'll get rid of this resistor right here. So, right? Huh? Yeah. Then we drop down right here, right? There's no such thing as this guy right here being bypassed, by the way. So we get rid of our bypass capacitor. Our coupling capacitor, if we're going to couple this output, would go right here. By the way, sometimes this is the actual load right here. And then we would come over here and then we would choose two resistors. These resistors right here are usually the same size. So what that's do is that's going to put, if I come up here and put plus 12, we don't even have to do the math, right? What would that put this right here? So what would VB be equal to? Shouldn't even have to get out a calculator. Two resistors in series, they're the same size. Total voltage has to be dropped in this circuit right here. Here's our first circuit right here. Right, you understand? It's a series circuit, 100K, 100K. What would be the voltage right here at that point there? Without taking your calculator out. The resistors are the same size. They have to drop the same voltage. 12 volts has to be dropped across the two resistors, right? So VB would be equal to 6 volts. Don't even have to take a calculator out, right? Everybody understand that? So what would VB be? Oh, I'm sorry. VE. Maybe 5.3 volts, and you take a calculator out so far, right? Okay. If this right here is a 1K, what's that? This is just a standard rule for two resistors. If they're the same value, I mean, I could come over here and I could have 100K, and I could come over here and I could have a 2K. I could come over here and I have 100K. These two resistors right here are going to drop the same voltage because they're the same size. Current is constant in a series circuit, right? You understand? So what we've done is we set up a voltage divider. I have two resistors that are the same size. They have to drop all the voltage. Since they're the same size and current is the same as a series circuit, the voltage that they drop have to be the same. So I've got to drop 12 volts in a circuit, right? Two resistors have to drop the same voltage. So what would they have to drop if they're the same size? 6 volts. So yeah, I mean, but if you was working in a series circuit and you calculated this guy right here dropped 3 volts, I would go over here and put 3 volts right there too, without even doing any math, because it's a series circuit. They're the same size. I is the same, right? You understand? So any resistors at the same size, once you calculate one, if you got multiple ones in a series circuit, what would you do? Just write them down. Well, here we've only got what? We only got 2 resistors in series. We're ignoring the 1K because it's seen as times beta. Typical beta for a 3904 would be equal to 100. So that means the signal coming in here would see this as a 100K, even though it's what? It's a 1K. So I come up here, I figure out my circuit. I would say my Rn would be equal to 1 over 100K plus 1 over 100K plus 1 over 100K, you're going to come up and get 990K or something like that. I'm sorry, you're going to get 99 or 97K, right? You understand that? So for all practical purposes, if we choose this resistor right here at the right side, we just ignore it when we calculate what? This circuit over here. So we just ignore it. And in real life, if I was an engineer, I wouldn't ignore it. But all we're trying to do is just get a pretty good idea of what this right here is supposed to be. So we say 6 volts. You know, if it measures 5.4, we're going to say that's okay, because we deal with a lot of approximations and transistors, because every one of our devices have what we call a tolerance. So I go ahead and calculate these for 100K. So what's the odds of that being exactly 6 volts? Slim to none, right? You understand? Because these resistors have 5% tolerances on them. So what's the odds of them measuring exactly 100K? If you had a precision meter, you know, 6-digit meter that you pay thousands of dollars for, there's no way in the world you're going to measure any one of these resistors that measure what? A 5% resistor that's going to measure exactly its color-coded value. So what we're doing, guys, is we're using a lot of approximations. So we're not getting the exact answer, but we're getting an answer that's what? Close enough so we know if it's what? If it's right or if it's wrong. So now I come over here, I got 5.3 volts. Now my input voltage can be real high, guys, because that sucker can almost be 10 volts peak. I'm sorry. It could almost be 10 volts peak coming into this thing. Can't put that into a common emitter. Common emitter, it's got all this gain, right? You understand? But what we're trying to do out of this thing, so if I put 10 volt peak to peak in, what would my peak to peak voltage be out? That's the beauty of this thing, guys. This is the beauty of this thing. It's in the emitter. I've already taken out the 5 volts, right? I've already taken out the 5 volts. So I would get almost 10 volts peak to peak out of this sucker. You don't get a voltage gain out of this. It's not going to, we lose this thing we call RE prime, so we're not going to get exactly what we get out, but it's going to be really, really close, because RE prime is going to be pretty small, right? You understand that? You get 10 out, almost 10 out. It's going to be a little less, because the only thing that we're going to get a voltage drop on is this thing called RE prime times beta. So if I come up here and calculate RE prime and it comes up to be 100 ohms, then it's going to see it as 100 ohms times 1,000, right? You understand? So that's what my input current is flowing through. So this guy right here, guys, so what's my input resistance? If you do this formula right here, what does it come up and give me? Yeah, for the impedance, RN. Because we're ignoring this. If we size that capacitor correctly, we can ignore it. And engineers are going to do that, right? You understand? So this is why these coupling capacitors, you'll see them up in the higher range, probably 100 microfarads or above. 100 microfarads is pretty standard. I think we calculated, if we used 100 microfarads, we calculated at 30 hertz, it would only have like 53 ohms worth of resistance, or impedance, I'm sorry. So 100K in parallel with 100K, so I'm going to take 100K, right? Yeah, see that? See that? So 99K. Okay, so I've got 10 volts peak to peak. What would that be RMS? 10 volts peak to peak. What would that be RMS? So that would be 5 volts peak, right? You understand? I'm going to come up here and divide that by 0.707. I'm sorry, 5 times 0.707. 3.53. Now over here, so that would mean that my input current is going to be 3.53 volts, my RMS input current, if I put my meter on there, divided by 99K. So what's my input current going to be? 35.7 microamps. Now my output current, if this right here is my load, we're not going to couple it right there right now. My output current would be 3.53 divided by 1K. So what's my output current? .53 milliamps. So my current gain, my AI, would be equal to 3.53 milli divided by 3.57. Well, we use 3.53 over here since we use it over there. Micro. What would be my current gain out of this amplifier? This is milli, I'm sorry. Milli. So if I write this big, so AI, this should be lowercase by the way, because it's AC, would be equal, I'm getting 3.53 milli out. I'm putting 3.53 micro in. Somebody came up with 3.57, but that's okay, guys. What would be the gain on this? What would be the current gain on this guy? So my current gain on this sucker would be 1,000. So what we get out of a common collector, guys, is we don't get any voltage gain, but we get a what? Ton of current gain. We get a ton of current gain out of these puppets. So these guys would feed a low impedance load. These guys are going to give us a lot of current, right? You understand that? No voltage gain at all. In fact, the voltage gain is going to be slightly less than 1. But normally we say 1 because it's what? It's so close. So the only thing we lose is that voltage drop we get through RE prime. So guys, I get a ton of current gain out of these things. So these are your drivers for your speakers and stuff like that. These amplifiers, these guys, if you're dealing with audio and you're driving a speaker is only like 8 ohms, right? You understand that? Car speakers are 4 ohm speakers. House speakers are usually 8 ohm speakers. So you can't take your car stereo out of your house and run your 8 ohm speakers. You could, but you wouldn't get what? You wouldn't get maximum power transfer. So to get maximum power transfer, you want your what? You want your output impedances and your input impedances to match. If you took your 2 ohm speakers out of your car and put it on your house stereo, you're going to put it on your TV, you're probably going to get what? Crummy sound, right? Because you've lost your impedance maximum. So what we're going to look at now is we're going to come up here and take this and we're going to add this to our power supply. So I'm going to come over here and I'm going to take a Zener, my Zener regulator. And this guy's not hard to design at all, guys. And then what I'm going to do is I'm going to come over here and I'm going to use a common collector, right? And I'm going to tap off and put that right here. And what I've got is I've got a regulated power supply that I can get a lot of current out of, right? You understand? So the problem we have with a Zener power supply by itself is the range of currents that we can handle, right? You understand that? So if this is a 5.7 volt Zener, what would this thing regulate at? So what I'm going to do now is I'm going to come out here and put a load right here. And let's say this is a 3904. We wouldn't use probably wouldn't use a 3904 for this guy because we want a lot of current gain out of it. And the typical beta is around 100. Y'all measured in one of your labs. You'll see it's around, you get around 90, or you'll. And my input over here, we want it to go from, let's say 200 milliamps through 500 milliamps. So this would be a 5 amp supply. And the 3904 won't handle this, guys, because I think the maximum current that this guy can handle is around 100 milliamps, but that's okay. We'll just try to figure this out, and we'll look at a transistor later on. So the minimum beta we should expect out of this would be 30, right? So what would my Zener see change over here? My Zener would see a change of between what? So beta is equal to IC over IB, right? Okay. And then we can rearrange this if we know one formula. Beta would be equal, beta would be equal to IC over IB. And some of y'all are still missing that on that test. And I don't know how to teach this, guys, but the largest current in the transistor is the emitter current. And we still had a 40% rate on that one little question right there on the test. And I don't know how else to teach that. So what's the largest current flow in a bipolar transistor? What's the largest current flow in a bipolar transistor? What's the largest current flow in a bipolar transistor? Okay, y'all think y'all gonna miss that on the next test. So 40%, twice this has been on there. And the formula is IE is equal to IC plus IB. That's the formula right there, guys. That's a C. You can rearrange that if you want. So what we do over here, if I know my collector current is changing between this range right here, what would I do to solve for the base current? Well, IB is going to be equal to IC divided by beta. And we'll use minimum beta. So I'll use 200 divided by 3. That would give me my base current. What's that going to be? I'm sorry, divided by 30. This is guaranteed, but we know we're going to get higher than that. And then I'm going to use 500 divided by 30. Huh? $66.6 million. What's that? Okay, 67 milli, right? And what would it be for 500? 66.6, which is 67, right? We're going, well, we usually round this up to size this resistor right here. And what would be 500 divided by 30? So what I would do, guys, once I figured out the beta of the transistor, these are the currents I would use inside that resistor. I wouldn't use these over here, right? You understand that? That makes sense? Now, by the way, So if I put 5.7 volts right there, what would I get out over here? Yeah, across my load. Approximately what? Approximately 5 volts. Yeah. Now 3904 wouldn't work here because the 3904 cannot handle 200 milliamps. I think the maximum current on the 3904 is, let's look real quick. Instead of me talking off the top of my head. Dang it. Yeah, the continuous is 200 milliamps. The problem we have, guys, is if you're trying to figure this thing out, is here we got to look at another situation. It's where's our maximum power at? Depends on which one you get. So you can get a PZT 3904, which can dissipate 1,000 milliwatts. Standard 3904 is 625 milliwatts. So the problem we have with this guy right here is over here we have unregulated. So let's say we're going from let's say we're going from 7 to 9 volts over here. Now over here we're going to have what basically all the time? 5 volts. So that means worst case that transistor, worst case, would have to drop 4 volts. Right? If it drops 4 volts and it's got a current flow through it, it's going to do what? It's going to create power, right? You understand that? So what's the maximum power in this circuit right here with this thing dissipate? Well, I would come over here and I'd take the maximum voltage it has to drop, which is what? No, yeah, 4. The maximum voltage is going to drop, right? You understand that? Which would be what? 4. I would multiply that times the maximum current my load is designed to handle. And then this would give me the power. So when you look at these series pass, by the way, this is a common collector, also called a emitter follower, but most people in power supplies calls this a series pass transition because all your load current has to pass through this, right? Series pass. They call that a series pass. But the transistor is a common collector, or all we call an emitter follower. So what would be my power up there, guys? Huh? 2 watts? Well, we couldn't use a 3904, right? So we'd have to find a transistor that can dissipate we would probably go about a couple times higher than that. So probably 4 watt transistor that had a beta meter, and then we'd have to choose it. These guys, the formulas that we basically already know, we could almost use to calculate this. So you can see this would be a very advantageous to take a Zener and get a regulated power supply using a common collector amplifier, right? Because we're not looking for a voltage gain, right? What are we looking for? Yeah, we're looking for a current gain. So this is a pretty standard power supply. Okay, so where are we? Where's our input at? Where's our inputs at? I'm sorry, where's our input at? It's on the base. Where are we getting our output at? Off the emitter. And that's the way you describe them, guys. Is you look where your input on, and you look where your output's at, and the other lead is common to the signal, not to the power supply. It's common to the signal, right? Y'all understand that? So this over here is staying pretty constant. But if I was to come over here and look at the other amplifier, the first thing you do to figure this out, guys, the first thing you do is look where your input comes to, look where your output is taken from. The other lead has to be common. Now, the way these things got this name is, I'm listening. Well, what we did is we looked at the voltage on the left, which I said was between what? Yeah, I didn't. I said it was between 7 and 9. Between 7 and 9. I looked at what my output is being regulated. What's my output at? 5. So when we talk about voltage drop, so what would happen is I would come over here with my meter and I would measure over here. Of course, we'd have to know this. If I measured 9 volts over here and I measured 5 volts over there, what's it dropping? 4 volts. So when we calculate the power on the series pass transistor, we take the maximum we're going to get on our unregulated. We subtract it from what we get from our regulated, and that tells us what that series pass has to drop. And if it drops a voltage, it's going to do what? It's going to use power. And this is one advantage a switching power supply has over a linear power supply, is that you're going to have this series pass right there. And when you have that series pass, it's going to get hot, guys, because it's going to dissipate power, right? And it's got to carry the load current. So if you think about this, if I'm trying to build a 1 amp supply, then we're going to have to really use a pretty good transistor. In fact, we might come up here and use a couple. You'll see some power supplies doing this. It'll be easier, guys, up as to the oops. What did I just do? So we have this transistor arrangement like this. You come over here, you'll see this used a lot. Where we take the base of one transistor and we hook it directly into we take the emitter of one transistor and hook it directly into the base of another. Anybody remember what we call this? And you can buy these guys. You can buy them inside a package. So notice, all we need is 3 leads. So I can buy this, and it'll be a 3-lead device. We can buy these in one transistor. So what do we call this arrangement? It's got a name. Anybody remember? I've talked about it before. This is called a Darlington pair. And if you look, we have 1 lead right here. We have 1 relay. It's got 3 leads. So you can buy these in a 3-pin pack. I think I told you my story about working on a printer, and in the schematic they drew it like that. And this is back in the days where we couldn't break over 2 junctions. So when I was checking this thing, my meter measured overload right there. So what did I do? I replaced it and put a new one in there, and it still did exactly the same thing. So what I did is I went in and I looked it up, and it was a Darlington pair. And my meter would not measure this 1.4 volts right there. Some of y'all's meter wouldn't turn on an LED, right? And so you couldn't check. If you've got one of those meters, you cannot check a Darlington pair, because my meter would have to put out at least 1.4 volts to do what? To break over those. So we can buy these things. Now, what do we use a Darlington pair for? Well, if this guy right here had a beta of a 30 and this guy right here had a beta of a 30, what would be the total beta of the circuit? So if I had two amplifiers and I got a gain of 10 out of this amplifier and I got a gain of 10 out of this amplifier, what would be the total gain out of the amplifier? Huh? You're killing me. So if I put 1 volt in here, I would get 10 volts out of there. So I'm putting 10 volts into there. I get a gain of 10 over there. I would get a gain of 100. So gains are multiplied together. They're not added. They're multiplied together. So it means in this Darlington pair right here, I would get a gain of 900. So that means if I put 1 milliamp right there, I would be able to get 900 milliamps out of this, a minimum. These are minimum betas, guys. These are not maximum betas. Y'all understand that? So you'll see this a lot. We'll come over here in my power supply. You'll see this a lot. But you got to compensate for it on your Zener. So I come over here and I have my Zener right there. Then I'll come over here and I'll run this through a Darlington pair. And this would be Darlington pair. So a while ago we were doing a power supply that was going from, so let's say I'm going from, let's say my current's going from 0 to 1 amp over here. And over here I'm using a 6.7 volt Zener. What would I regulate at over here? So it's going to be 6.7 minus 1.4. We're going through two junctions, right? What's that? 5.3. So this would still be a good 5 volt power supply, right? You understand that? If this had a beta of 30, this had a beta of 30, then my maximum current flow out of my Zener would be equal to 1 amp divided by 900. So what would be my Zener current over here? One divided by 900, guys. Not too hard, right? 1.1 milliamp. So my Zener would only handle 1.1 milliamp plus IZK. So my Zener would regulate really, really well, because over the entire range, this guy's only going to change from what? About 1.1 milliamp, right? You understand? So my Zener would regulate really, really well. But you got to remember that you're going to lose about what? 1.4 volts So you can buy Darlington transistors. I mean, let's go on here and they got 3 leads on them, right? So we'll just look at Gamaco, which is where we get most of our transistor parts. And then we'll talk. So 39 cents for this guy. It's got a 5 amp, 60 volt, TO92. We could look up the data sheet on it. But this guy here's 3 amp, 3 amp, 3 amps. Let's see if we got the data sheet on it. Let's see what the beta on this thing is. Typical beta on this sucker, typical beta is 2,500 at the maximum IC. So that means my Zener is going to regulate really, really well, right? You understand? Because the current flow through it's going to be almost constant between minimum and maximum current. 2,500. So this is that you're going to run into a lot of Darlingtons inside your power supplies. Because now your regulator, the guy that's actually giving you the regulated voltage, is going to have to supply almost no current at all, right? You understand? Which means it's going to regulate really, really well. You're going to run into Darlingtons in stereo circuits because you get extremely high gain out of these things, right? So this guy right here is so you got different ones. Sustained breakover voltage, 60 volts. We'd have to look that up. And then, of course, when you saturate this thing, it's going to drop, says it's going to drop 2 volts, around 4 volts at 5 amps. So that's something you'll have to take into consideration too. So these common collector amplifiers, also called emitter followers, why do we use these guys for? What type of gain? Of course, if we get a current gain, we're definitely going to get a power gain, right? You understand that? But these guys we use for current gains. A lot of current. Huh? Well, we could use Darlington pairs in a common emitter. We usually wouldn't run into that. But primarily, it's not Darlington pairs. It's common collector amplifiers. We don't get a voltage gain out of them. So what's the voltage gain out of a common collector? What's AV of a common collector? About 1. Yeah, approximately 1. We use 1 all the time because the only difference is what we lose through RE prime, but it's approximately 1. So what do we get out of this thing? Your power gain is always going to be greater than 1. I'm sorry. Your current gain is always going to be greater than 1. And we're talking about, I think on our current gain a while ago, that sucker had a current gain of what, 1,000, right? You understand? So these are going to be the drivers for low resistance circuits like power supplies. Power supplies are going to drive low resistance circuits, right? You understand that? Amplifiers, you know, like what we talk about, audio amplifiers, these guys are going to drive low resistance devices, right? You understand that, which require a lot of current. Solenoids, you know, I can drive a solenoid off this. I might want to drive a relay off of this, a DC relay off of these things. Like I said, that's what they were doing on the printer that I was working on. They were using the Darlington pair to energize a relay because they got a real high watt out of these things. Yeah, so these things typically they have a high input impedance. They have a really low output impedance. they have a gain of, they have a voltage gain of approximately 1, and they have an extremely high current gain. So we're going to use these guys to drive low impedance circuits, right? You understand? So we'll be able to take the high impedance output of a common emitter, and we could run that into a common collector, and we could drive speakers with it. So what we do, the advantage of a common collector, a common emitter, is we can get both a voltage and current gain out of that. But these things have a moderately input impedance. They have a real high output impedance because that big dang collector resistor we got to put out there, right? You understand that? So these guys can't provide a lot of current, but they can step it up high enough so we can pump this into a current. We can pump this, we can take the output of a common emitter. So I might do this, this might be a common emitter amplifier, and then I might feed that into a common collector amplifier, right? You understand that? So I use common emitters to get my voltage up and then enough current to drive these things, and then we usually, to drive a low impedance load like a speaker, we're going to output off a common collector. Common emitters can't drive speakers. Y'all understand why? Because I take a 1K resistor right here, and then I output that into an 8 ohm speaker. Well, that 1K resistor is going to drop all my voltage, right? Because we got to have that collector resistor up there to set our mid bias point. Mid bias point on a common emitter, on a common collector, you just use basically the same size resistors over there, right? You understand? Very easy to bias that. We usually choose them pretty big to increase our input impedance. So the other day I did 10K, but notice today I did 100K. And they're usually about the same. If you want to bias it directly in the center, so what they'll do on a lot of audio amplifiers is you'll see that they'll have so they'll come over here, and this right here might be 100K, and then down here they'll use maybe a 250K resistor down a pot wired as a rheostat. And then what can they do now? Well, they could come up here and set this output voltage at exactly, if this is 12 volts, they could set that sucker exactly at what? At 6 volts. And that's where we'd want that to be setting at 6 volts, right? You understand why? Because that means I can swing it as much up this way as I can do what? Yeah. And if we overdrive it, it would clip on the top and the bottom first if the input tries to go up above. So guys, these are the two most popular amplifiers we have is the common emitter. Because what can we get out of a common emitter? We can get both what? A voltage gain and a current gain. But they cannot drive a low impedance load. They can drive a high impedance load, but they can't drive a low impedance load because of that dang collector resistor we have to put up there, right? So what we have to do is we have to have that collector resistor up there. And we can't make that real low, right? You understand? So that collector resistor up there limits the load that we can drive. But we can take this and drive a high impedance load and get a little more gain, right? And then eventually, if we need a lot of current, we'll eventually hit a common collector amplifier. Also called emitter follower. Y'all know why it's called that name? Because the emitter follows the input signal. So they're going to be in phase with each other. Another thing that we get out of a common emitter, when we come over here and put an input signal in this that does this, the output signal is going to do this. So what we get out of a common emitter, the input and outputs are always 180 degrees out of phase. On a common collector, the input and the output are in phase with each other. So if I got it on a common emitter, what we would see is we would have a gain we'd have a voltage gain between the input and the output. If I did it across a common collector with an oscilloscope, those guys right there are going to almost sit right on top of each other. The output's going to be just slightly less, right? You understand? So, common emitter. On some of the characteristics of common emitter. We have a moderately high input impedance. We have a high output impedance. We can get both a voltage and a current gain out of these things, which means if we get a voltage and current gain, we're going to get a power gain, right? The input and the output are 180 degrees out of phase. What's the characteristics of a common collector? Pretty good, pretty high input impedance, very low output impedance, right? We get a voltage gain of about 1. We get a real high current gain. So we use these guys to drive low impedance loads. It has a moderately high input impedance. So a while ago we had 99K, right? You understand? It has a low output impedance, right? So we would use these guys to match a high impedance device to a low impedance load. So that's a common collector, so a common emitter. So I would use this, if I was having a stereo amplifier, basically what we do is we usually go through different stages. By the way, this is the generic symbol of an amplifier. In digital, you learn it as a buffer. No, not because there's no suckers, there's no circles. In analog, this is the basic symbol of an amplifier. So this might be a common emitter amplifier, but this would not be bypassed. So what we do is we lower the gain, but we get a real high input impedance. And then this guy right here would probably be bypassed. And this would still be a common emitter. That way we can get the voltage gain way up. And this one right here would be a common collector. And we never have a bypass on a common collector. Now we might have more. So this is the basic 3 amplifiers would probably, most of do now, we hadn't got there yet, is normally what we would do, our first amplifier would probably be an FET. Because these guys have almost infinite input resistance. So we'll get into FETs a little bit later once we get a pretty good. But this would probably be the makeup of a stereo amplifier. And this guy right here, by the way, this guy would probably be an AB amplifier. These right here would be Class A amplifiers. And what output on the AB amplifier, which we'll talk about. So we'll go through the other classes of our amplifiers. So what did we talk about? So what's a Class A? So Class A, your output, we get 360 degrees of the input signal. Class B, we'll look at the circuit later, you only get 180 degrees of input signal. So what y'all think of Class C? This is going to be less than 180 degrees. And then an AB is going to be, there's going to be 2 Class Bs. That acts like an A. So if I was looking at the output of a and we're going to use a sine wave here, guys, even though audio is all over the place, right? So if I was looking at audio, I'm gonna try to figure out how to show y'all this while we go to lab. But so if I had a Class A amplifier, if I was bringing this garbage right here in, which would be audio, then I would be getting that garbage right there out. Now, if it was a common emitter, it would be 180 degrees out of phase, but it would be a mirror image of the other one, but it would be bigger, right? You understand that? If this was a Class B amplifier, and I was bringing this garbage in like that, then what we would get, guys, is we would only be getting one side of it. Because what would it do? It would flip off the other side. So if I was bringing in a sine wave like this, then on the output, if it's not a common emitter, on the output, maybe we'd only be getting the positive pulse out. And then a Class C, if I was bringing in a sine wave, we would only get a small portion out. So what we'd only get would be something like that. So if I was bringing in a Class AB, what I would do is I would design this one so it would pass the positive. So I would these right here would be hooked together. And then what would happen is this guy would give me this out. I would design this one to pass the negative. This guy would give me this out. And when we combine them both together, what would we get? Well, that's a Class AB. So this would be a Class B. This would be a Class B. But it develops an output that looks like a Class A. We'll look how we can do all of these. We'll talk about what we use Class B for, what we use Class C for. And anything above Class AB, these are going to be digital. These are going to be your pulse width modulations, your frequency pulse train outputs. Those are going to be anything above that. So in here, all we're going to do is look at these amplifiers right here. So when we do a saturated switch, it's going to be something above a Class A, Class B, or it's going to be like a Class D or something like that. Does that make sense? So these are just the introduction of these four classes of amplifiers that we're going to be dealing with. We're not going to be designing them. We'll go through one to show you how we can do the calculations, but we won't require that in class. Basically, we're almost through with bipolar transistors on what we're going to cover. I'll give you the characteristics of a class of a common base. You're not going to run into common bases very often because common bases you don't get a current gain out of those. You get a voltage gain. So common emitter we get both a watt and a current. Common collectors we get common collectors current only. A common base we get only a voltage gain out of the common base. So don't get a voltage gain. And that's why it's called emitter follower, because the emitter is following whatever's on the base. Right? You understand? You get a voltage gain out of the common base. Yes, that's all. Yeah, common base. We'll draw. Common base is real weird. So common base, you're going to input on the common base. We input on the emitter. We output on the collector. So that means my emitter current and my base current, my emitter current and collector current are basically equal to each other, right? You understand that? So if we input on the emitter and output on the collector, then somehow the base has got to be common to the signal, not to the power supply, to the actual signal coming in. So common bases are, we use common base for extremely high frequency applications. So you're not going to run into a common base that often. Our main amplifiers we'll look at. But you need to know the characteristics in case you run into it, right? So if I get a current gain, I can get a power gain, right? You understand that? If I can get a voltage gain, I can get a power gain. If I can get a voltage and current gain, then I can get a pretty good power gain. But the biggest problem we have with the common emitter, so you say the common emitter looks like it's the guy to go, but the common emitter has an extremely high output impedance, right, relative to what we need to drive. So common emitters are great to get where we need to get, but if we need a lot of current, and a lot of power, then we're going to do what? We're going to use that common collector as our output. So you're going to run into these guys marrying together. So what we do with our common emitters is we use our common emitters to get that voltage up high enough, right, and just enough current to drive what? A common collector. So a common collector, we don't get any voltage gain. The only thing we get is what? Current gain. And that's what we want out of a power supply, because now our regulator can be a little old tiny regulator, and then we can run that through a couple of transistors and we can get a ton of current out of these things. Like a 3055, that sucker's rated, it's rated at 15 amps. I'd have to look at the power. 15 amps I can get out of that thing. Right? So we can go, and that's what I'm using on my power supply. So I built an 8 amp power supply at the house. It's not working right now because I blew out my regulator, but I could bring it in and show you that. In fact, I need to bring it in and fix it. I keep putting it off. I made it out of a golf cart charger. So I took the big old transformer that came in that charged a golf cart, and then I designed a power supply around that. So you could probably get one of those for nothing, almost nothing. The guy down on 15th Street, the guy that sells used batteries, he also deals with golf carts. And you might could get a golf cart charger down there and make you a sure enough power supply. Mine's a variable power supply, and I'll give you a little hint of how to work on that if y'all want to design your own power supply. It's not as complicated as you think, because a lot of our circuits are already built for us, right? You understand? Because power supplies have been around so long, we've got regulators already out there. We don't have to use Zener's anymore. We can use a fixed regulator. Use those. So any questions? So what do we need to do? We got to get some labs out of the way, guys. So we got the common emitter lab, and then we got a common collector lab. I might let y'all do the common emitter just to get a hint of how you would wire those things. The common collector lab is not in your book. It's going to be, so that's a handout lab. And I think what I'll probably do is we'll wire that up, and we'll do that as a class lab instead of individual teams. And that way, you don't have to wire it. All you have to do is just make measurements to see if everything works out. Okay, guys. Any questions? Okay, guys, y'all can take a break and then